All right, we've kind of covered this in the last lesson, but today we're going to have a longer look at stationary points or zero gradient points. And again, just name them. So recall from last lesson, this thing here, we call this a local max. Okay, it's not the absolute max, it's the local max. Kind of in this area, that's the maximum value. This one here we call a local min. And this one here we call a point of inflection, and we're going to assume that this is a stationary one. Now, a bit more on stationary points. This question here, recall that you can have a point of inflection that's not stationary. So if we get this function here, I can't remember what it was. But this is the function here. So y equals negative x cubed, take 6x squared, take 13x, take 11. And we can see here that we've got a stationary point, not a stationary point, a point of inflection. Is it a stationary point? Well, dy dx equals negative 3x squared, take 12x, take 13, and we'll sub in 2, so dy dx with x equals negative 2 is going to be negative 3 times 4 plus 24, take 13, which is going to be negative 1. So notice there that the gradient at x is equal to negative 2 at the point of inflection is negative 1, not 0. So therefore, it's not a stationary point. It's a point of inflection, but it's not a stationary point. Okay, so on to sign diagrams, and these can be really useful for unfamiliar functions. So familiar functions, you should be able to use it by pretty much like guess and check, but for unfamiliar functions, a sign diagram can be really helpful. Right, so let's note that f of x equals 2x cubed, take 6x plus 1. F dash x is equal to 6x squared, take 6. And we're going to go 0 equals 6x squared, take 6. 6 equals 6x squared. 1 equals x squared. X equals plus or minus 1. Right, so what we do then for the sign diagram is we're going to put down negative 1 here and 1 here. Now what we do is we choose a point to the left of negative 1, i.e. negative 2, a point to the right, which is 0, and a point to the right of 1, let's say 2, 10, 15, 100, whatever you want. And what we're going to do is work out what the gradient is at this point. To speed up the process a little bit, because you don't want to watch me do a whole heap of substitutions, I'm just going to define f of x and do it on my calculator. 2x cubed take 6x plus 1. So I'm going to diff it, diff f of x, and I'm going to sub in x is equal to negative 2. And f dash x at that point is 18. It's got a positive gradient. Okay, now when I change this to negative 1, hopefully you know what's going to happen. It should have a 0 gradient, and it does. So we're going to say that it's 0 there, which means we've got a horizontal line. Now what should happen here is that we should get a negative gradient at 0. Let's see if that happens. Indeed. And so what's going to happen is that our cubic is going to give us this shape here. So it's going to go positive, 0 gradient, negative, and we should have another 0 gradient and then a positive. So let's do both of those at the same time. So f of 1 should be 0, or f dash 1 should be 0, and f of 2 should be positive. It is, it's 18. And that gives us an idea of what is actually going to happen with this function. So it goes, or it has a positive gradient, 0 gradient, then a negative gradient, 0 gradient, positive gradient. So it gives us an idea of the shape. Now again, with cubics, you can do that by sight, hopefully, but sometimes there's some weird functions that are cobbled together. You just don't know what they're doing at particular stationary points. So it can be useful to use one of these diagrams. I think it's called a sine diagram, to ascertain what the shape is. Okay, but if you don't need that for a cubic function, that's actually good. We don't really need this column. All right, so what we've got is a function, it's a cubic function, a negative cubic function, and we want to get the coordinates and nature of stationary points. So let's find where the stationary points occur and what type of stationary point is it, i.e. local min, local max, or stationary point of inflection. Okay, so to do that, what we're going to do is let the derivative equal 0 because the gradient at the stationary point will be 0. So let's get the gradient function first of all. Okay, now what we'll do is let the gradient function equal 0. Divide both sides by -1 just to make it, well, I feel like it can make it a bit easier to factorize. Um, 6x, 2x. And x is equal to -2. All right, so let's do f of -2. So when I put -2 in here, I've got -8. -2 squared is 4. 4 times -2 is -8. Take away -2 is, it's going to be plus 8. Let's just double check that on the calculator. All right, not bad effort there. Okay, so I should be able to, if I teach this subject, sub that in. 2 on 3 equals 4 lots of 2/3 is 8/3. Take away, all right, 2/3 squared is, so let's go 2 lots of 2/3 squared is 4 on 9. Take away 2/3 is 8 on 27. Okay, equals 8 on 3, take away 8 on 9, take away 8 on 27. Okay, times 9 times 9 times 3 times 3. So ultimately this is going to be 9 8s are 72, 8 3s are 24, 8. We're going to add these together and that's going to be negative that amount. So we've got 10, 14, 1, 7, 9, 10, 104. Negative 104 over 27. I'm not that confident about that one, but let's just do it anyway. F of 2/3, 40 on 27. What have I done wrong? Okay, not a great effort there. That's supposed to be 72, and then we're going to remove 24, and then we're going to remove another 8 from that. So let's remove 24 from 72 first of all. 8, 4, and now we're going to remove another 8. So 48 take 8 is 40. So that should not be that. It'll be negative 40 over 27. Okay, so our coordinates are as follows. So we've got -2, -8, and we've got 2/3, comma, -40 on 27. Right, and it's a negative cubic. Negative cubics look like this. So the first one will be a local minimum, the second one will be a local maximum. So this is the first one here, so that is a local min, and this one here must be a local max. Okay, so that's why it's really important to know your general shapes of functions here. So you know that that's a negative cubic, you'll know that it has to take on that shape. All right, so let's just check out the next part here. So we're looking at when is the function increasing. Okay, so because it goes like this, and I don't know whether this is the overall shape, let's just say that it is -2 and 2/3, it's going to increase between there and there. Okay, now this is actually saying when is the gradient positive, or when is f dash x greater than 0. Okay, so for this particular question here, what we do is we actually say that it's going to be between -2 and 2/3, but we don't include those endpoints because that's when the gradient is 0 and we want a positive gradient. Now, so x is an element. All right, now x is an element. When is it decreasing? Well, it's this part and this part here. So that's between negative infinity to -2, not including the -2 because that's a 0 gradient point, union with 2/3 to positive infinity. Now, different question, when is it strictly increasing? Well, strictly increasing means given any 2 points over this section here, -2 to 2/3, if you take 2 points and put them in, what you'll find is that one will be larger than the other, and that also includes these endpoints or the 0 gradient points. Okay, so what we do for strictly increasing is we include those square brackets there. So it's important to really carefully read the question. Increasing functions, or when f dash x is greater than 0, we don't include the endpoints, but for strictly increasing, we do include those endpoints. And so for part B, x is an element. It's going to be still don't include negative infinity, but we square bracket those endpoints. Okay. All right, so there's your questions there, and don't forget to use the calculator for those ones.